Hi everyone, my name is Ohad. I'm a student at Yaron Bromix Group at the Hebrew University. And in this talk, I'm going to describe our recent work on thermal biphotons. And I'm going to start with a very brief reminder on thermal light and the Henry-Brown twist or HBT effect. So consider a thermal light source of size capital D, consisting of an ensemble of emitters. Each of them emits light with a random and fluctuating phase. So if we look at the far field with a very fast camera, we would expect to see something like that, a speckle pattern, which is a random interference pattern due to the random phases of the emissions. And the speckle pattern will fluctuate over time due to the low temporal coherence of the source. What HBT did is that they performed a measurement in which they had two detectors at some separation, and they measured the intensity correlations between these two detectors. What they observed that if you look at the intensity correlations, or the second order coherence function G2 as a function of the separation between the two detectors, you get that if the detectors are close, you get a bunching effect in which you have intensity correlations which disappear when the separation is large. This could be understood what is called the fluctuating speckle interpretation of HBT. If the two detectors are within the same speckle grain, which is of size lambda over capital D, inversely proportional to the size of the source, then the intensity will be correlated. If the detectors lie on different speckle grains, the intensity would not be correlated, and there will not be any intensity correlations. It's important to note that for thermal light, we have the Sigurd relation, which relates the second order coherence function G2 to the field correlation or first order coherence function G1, so that G2 equals 1 plus G1 squared. In the lab, one typically uses a so-called pseudo-thermal light source, consisting of a laser shining a rotating diffuser, which randomizes the different phases. And the same HBT effect will appear. In this talk, we describe something we call thermal biphotons. Thermal biphotons, you can think about it as a source, still of size capital D, but now instead of different emitters that each of them emit single photons with random phases, now we have correlated emissions of pairs of photons. So each emitter of typical size small d, lowercase d, actually emits pairs of correlated photons. We implement this kind of source in the lab of pseudo-thermal biphotons by using the process of spontaneous parametric down conversion, or SPDC, in which we have a classical pump beam, and with a nonlinear interaction with a crystal, pairs of photons, correlated photons, are created, and these created photons are spatially correlated so that are emitted within the same area, small d. So capital D is determined by the size of the pump beam, and the two photon emissions are determined by the spatial correlations of SPDC. And again, we pass the photons through a diffuser that randomize their phases. So now if we take this kind of source and we measure the intensity correlation or coincidence counts at the far field, measure an HBT type experiment, we'll obtain something like that. For a static diffuser, we will get a two-photon speckle pattern, the so-called two-photon speckle pattern, because we have emissions of pairs. And the size of a speckle grain, as before, will be inversely proportional to the entire size of the source, capital D. Now, if we rotate the diffuser and look at the ensemble average results, we will get that still G1, the first order coherence, drops on a scale of lambda over capital D. However, the HBT peak, we still observe an HBT peak of 2 to 1 for thermal biphotons, but the width of the HBT peak does not depend on the entire size of the source, but rather on the spatial correlations at the plane of the diffuser. So we get two things here that are different. First, the classical speckle interpretation of the HBT effect breaks down because we cannot say that the photons are correlated only when they are within the same speckle grain. And the Sigurd relation is broken as these two curves does not have the same characteristics. To get a bit of intuition on these results, we try to explain it using the so-called advanced wave picture of SPDC. Briefly, the advanced wave picture says that we can replace a quantum experiment like that where we have SPDC and we measure correlations between two detectors. We can replace one of the detectors with a source and look, we replace the nonlinear crystal with a mirror and we look at the back reflected light with a camera. And what we know is that the intensity that we see in this camera will be equivalent to the quantum correlations that we will measure in the quantum experiment. In our case, well, the quantum experiment is an HBT type experiment where we have the thermal biphotons and we measure the correlations. We can replace it with an experiment in which we send a laser onto a rotating diffuser and look at the back reflected light with a camera. While our original experiment is related to the HBT effect, in the advanced wave picture, it is related to a phenomenon called coherent backscattering of light. So what is coherent backscattering of light? Basically, if the diffuser was static, what we have here in the back reflected, we send light to a disordered media and we look at the back reflected light. So if the diffuser is static, we'll get some sort of a speckle pattern. And if you rotate the diffuser, we'll get one would expect to get a very homogeneous response, but we see here that we have a 2-to-1 peak, which is called the CBS peak. The reason for this peak is that in the back reflected, in the backscattering direction, there is constructive interference of reciprocal paths that cause this coherent effect to appear. So we actually establish a connection between the HBT effect in the quantum experiment and the coherent backscattering phenomenon in the advanced wave picture. And the breakdown of the classical speckle interpretation of the HBT effect is equivalent to the fact that the size of the CBS peak can be different from the size of a speckle pattern, of a speckle grain. Great. The last thing I want to talk about is the relation between our experiment and thermal biphotons to entanglement certification. So say we have some state psi that we want to check whether or not it is spatially entangled. What we will typically do is to measure in two bases. First, we can measure in the far field and obtain the momentum correlations between the two photons. After that, we'll measure in the near field to obtain the position correlations between the two photons. Having these two results, we can check if we can break some inequality. In this example, if the multiplication of the two uncertainties is smaller than 1. If we can show that this inequality holds, then we know that our state is entangled. Thermal biphotons actually allows us to do something else. We will still measure the momentum correlations in the far field, but now instead of near field measurement of the correlations, we can still measure the correlations in the far field, but put a rotating diffuser in the near field so that we replace the near field measurement basis with a disordered average basis in which we rotate a diffuser. In this disordered average basis, we know that we will get the HBT effect. And as we have shown before, the width of the HBT effect is determined by the near field correlations in our state. So we were able to establish a similar inequality. So far we prove it for pure states and we are working on the more general case. But if one can measure in these two bases and show this inequality holds, then we know that our state is entanglement. And indeed, in our experiment, we'll get that entanglement is indeed necessary to observe the results. So to sum up, we discussed what is thermal biphotons, a new type of source that we propose. It exhibits a 2-to-1 HBT peak, indicating that indeed these photons are thermal. However, the classical interpretation of the HBT effect using the fluctuating speckles is broken, and so as the Sigurd relation, which does not hold for thermal biphotons, we show that the HBT effect and coherent backscattering of light, both of them seemingly are unrelated with phenomena exhibiting a 2-to-1 peak, can be related to each other with thermal biphotons in the advanced wave picture. And we discuss an exciting new avenue towards entanglement certification using a disordered average basis. which we are very excited about. So thank you very much for listening, and I will be happy to answer all of your questions now, or you can contact me via email. Thank you very much.